Okay, we're going to start. Hi, everyone. Welcome and thank you for joining DataCon LA 2020. I am Tala Ghazale, your host, and our co-host today is Ed Choi. We will be moderating the chat and the Q&A for you during the session. I am very excited to welcome you to the Emerging Tech track. Our talk today is the future of Mars exploration, a tale of perseverance and curiosity, with our guest speaker, Dr. Anita Sengupta. Dr. Gupta is a rocket scientist, pilot, aerospace entrepreneur, and veteran of the space program. She developed propulsion and entry system technologies for NASA for missions to Mars, the main asteroid belt, and the re-entry to Earth. She is now a research professor of astronautics at USC, former SVP of a Hyperloop tech company, and founder of 2 electric aviation startups. Please help me in welcoming Dr. Sengupta. Dr. Sengupta, the virtual stage is yours.
Thank you so much for that wonderful introduction, and good evening, everybody, and welcome to my presentation, and thank you for listening to it. So tonight I'm going to talk about the future of Mars exploration, and of course my title is a play on words because the mission that I worked on was Curiosity, Mars Science Laboratory, and the new mission which is coming up, Mars 2020, the rover's name is Perseverance. So I am a professor at USC, and I've actually went to school at USC as well. I spent many years of my career working for NASA's Jet Propulsion Laboratory. So a little bit of my background, ironically, started on Mars and came back to Earth. I do have a PhD in plasma physics related to electric propulsion systems. And shortly after I got that, I actually shifted over to work on the Mars Science Laboratory mission, specifically on the development of the supersonic parachute, which is the image you can kind of see in the middle there of me in front of it. And then I started to work on things that were getting closer to Earth, which was a Venus entry, descent, and landing system, Earth reentry systems, and then eventually a payload for the International Space Station in low Earth orbit. Then I decided to actually leave NASA and go and work for the transportation sector and develop the Hyperloop, which is a ground-based form of transportation, and green transportation, and now focused on electric aviation, both in my research and in the companies that I have. And so my appreciation for Earth actually comes from having worked in the space program for so long. We have an amazing planet, so we have to do what we can to keep it safe here at home. But for the topic of the talk tonight, ooh, this thing got delayed a little bit. Okay. Is Mars. And the first question we have to ask ourselves is, why are we so interested in Mars? And there's two primary reasons for that. The first one, of course, is planetary science. And we're going to talk about that a little bit more. But Mars is one of the terrestrial planets. Venus, Earth, and Mars. And by understanding how those planets evolved, we can actually understand more about our solar system and more about our home planet, Earth. The second reason is that Mars is very likely the first place we will set up a colony off-world, off of Earth, because it has many natural resources that we can use, and it's more hospitable than, for example, being in the vacuum of space or even being on the surface of the moon. So where we go next as a species and set up sort of permanent habitation, my guess is probably Mars. And I'm also happy to answer many more questions on that topic as we proceed during the talk tonight. But to understand a little bit more of the properties about Mars, Mars is obviously smaller than Earth, which means that its gravity is only about 1/3. But when you compare that to the micro zero gravity environment of being on the space station, it's actually a lot easier on your body to have 1/3 gravity. It's all easier on plants to grow them as well, which might be necessary for food when we eventually set up shop on Mars. Mars does also have an atmosphere. The atmosphere is quite thin. It's only about 1% the surface density on Mars as compared to Earth, and that atmosphere is primarily CO2. So if we do end up sending people to Mars, which is the future of Mars exploration, we will have to have an oxygen supply to create air, and we will have to live in pressurized habitats to protect us from the environment on the outside. But when you compare that to the moon, and when you compare that to the vacuum of space, it's actually a lot easier to be able to set up the engineering technologies necessary to be able to survive. Now, Mars does get quite cold in terms of really cold temperatures during the wintertime, during the nighttime, as you get to higher and higher latitudes, but it also can get a little bit temperate, sort of like a California winter at the equatorial regions in the middle of the summertime. So it really depends on how you think about it, but it is still probably the most hospitable place that we can find. The radiation environment is a bit of a challenge, and we'll talk about that later. And ironically, the day on Mars is pretty close to the day on Earth. So from a human circadian rhythms perspective, it's not that hard to be able to adjust to a day which is 24.6 hours long versus 24 hours long. And people do that currently now when they do mission operations for the rovers, which are on the surface. But the reason that we send rovers such as Perseverance and Curiosity is to understand the prior geological history of the planet, both from assets which orbit, such as Mars Reconnaissance Orbiter, as well as rovers that are on the surface. And when we take a look at Mars from orbit, we can see some really interesting features. As shown in this graphic, on the top is Olympus Mons. It's actually the largest mountain in the solar system. It's an extinct volcano, probably about 6 to 7, or no, 3 times as high as Mount Everest. And then Valles Marineris is sort of the scar that goes across the center of the planet, which is about 6 times as deep as the Grand Canyon. So we know that Mars has had a really interesting active past in terms of seismic activity, volcanism, and potentially water flows on the surface. But clearly, something has changed. That seismic activity seems to have stopped. The water obviously has gone from the surface. So we need to understand what happened, why did it happen, and we can answer some of those questions by sending rovers and landers to the surface of the planet. So one of the theories about what potentially happened is that there is a remnant magnetic field on Mars, and that magnetic field was actually disrupted and destroyed by a asteroidal object that came in and smashed into the planet, shattering its core, therefore disrupting its magnetic field. And potentially that is the reason why it lost its atmosphere and therefore it lost its water. And as a subsequent aside, there's a mission called Maven, if you're interested in it, which has delved a little bit more into what happened to the atmosphere as a result of that. So one of the questions I like to ask people when we do in-person presentations is, does Mars have moons? So you can't raise your hand because I can't see you, but Mars does have 2 moons. They are satellites, Phobos and Deimos. They're quite small. They kind of look like odd potato-shaped objects because they're sufficiently small that they haven't sort of compressed under their own gravitational weight. But they are natural satellites, which you can think of a human mission architecture in the future, which could actually use them, where we would set up communications relays, for example, on the surface of moons, or even do mining activities on the surface of these moons. We know that they have all kinds of interesting minerals, which could help us to set up shop on the surface of Mars. So another question I like to ask people is, have we found water on Mars? Those of you who are Doctor Who fans will remember that there's an episode called Water on Mars, slightly different from that. But yes, indeed, Mars did have water on the surface, and Mars still does have water in the subsurface. So we believe, and there's a lot of evidence to support that with the measurements that we've made from orbit, that large bodies of water once flowed on the surface of Mars. And in these images here in the upper right, you can see looking at the polar regions, and we know from orbit we can see measurements of sort of salt water ice. And then the image on the lower left here, which is taken from underneath the Phoenix lander, which is roughly the 2005 timeframe, as it came into land and its engines were sort of pushing gas towards the surface. It actually exposed salt water ice right below the surface. So we know that there are subsurface quantities of water at different places on the planet. So that's really important when we think about in the context of resources that might be available to future human exploration. So another really interesting question is there water flowing on Mars today? So in fact, there is. It's not in the form of big torrential flows. It's in the form of wet mud. Some people refer to it as a putative water seep. And the reason why this happens is that Mars is tilted on its axis, which means that as it goes around the sun, different parts of the planet experience heating and cooling. So if there's a subsurface frozen aquifer, that can actually melt and come out of the sides of these cliff faces. And these images that you see here are from a spacecraft that NASA put up there several years ago called the Mars Reconnaissance Orbiter. Beautiful high resolution images of the surface. And you can see these black streaks coming down. Those are actually wet mud, which is flowing on the surface of Mars, either in the past or seasonally, which is the animated GIF that you see here on the left-hand side. And other measurements on board the spacecraft indeed confirm that there is water content in it. So it's a really important finding, because where there is water, there is potentially a life, and certainly it's needed for life and future human exploration. So from an engineering perspective, which of course is my background, I'm an aerospace engineer, all my degrees, we have something called entry, descent, and landing. You can't see my shirt, but it says EDL on the side. I was part of the Mars Curiosity entry, descent, and landing team. It's a really hard thing to do, and we've landed on the surface of Mars a total of 8 times. Our next landing, of course, is coming up in February of this year on the horizon. We've landed the Viking landers in the 1970s. There were 2 of them. The Pathfinder rover in the early 1990s, and then Spirit and Opportunity rover in the early 2000s, the Phoenix lander in the 2005-2006 timeframe, Curiosity 2012, which is the one that I worked on, Insight in 2018, which wasn't that long ago, and now we've got Mars 2020, Perseverance coming up, landing in February of 2021. And these images that you see represented here are images that the rovers and landers have taken of their landing site after they've landed. So it's pretty exciting how we've been able to do that so many times successfully. And the United States, NASA, is the only space program that has done this successfully. The Russians tried and failed, and sadly, the European Space Agency tried twice and failed. So it's a very difficult thing to do from an engineering perspective. And it gets a little bit easier over time because we learn from our prior attempts and we make it better each time. But then we also challenge ourselves by trying to do more interesting and difficult landing maneuvers each time. And so this really couples nicely to the engineering mindset, which is that you learn from the past and you build a future evolution of technology. So with that prior knowledge, with those lessons learned, we can actually increase the complexity of our landing systems and we can increase the size of our rovers. And so in this graphic here, you can see the evolution of rover technology over the course of the past 30 years. So the little Sojourner rover, which is in the lower left bottom, kind of looks like a little Tonka truck, which is basically the size of what it was. It was our first time doing a propulsive landing all the way to the ground since the Viking lander days. It was a solar powered rover. About a decade later or so, we sent something slightly larger, which was the Spirit and Opportunity rovers. They're about the size of a lawnmower, also solar powered, more mobile system, more science instruments on board. And then, of course, we had our step function increase with the Curiosity rover that was sent in 2012. The size and the weight of a small car, a Mini Cooper, is how it's best described as. Very large wheels, very robust platform so that it can basically climb over very complex terrain, large rocks, and carry more scientific equipment. So the Curiosity rover was the first time we actually sent a rover to a place that we really, really wanted to go from a scientific perspective because it was really hard to get there. And it carried a whole bunch of instruments on board, which allowed us to take very sophisticated measurements to assess habitability. The Mars 2020 Perseverance rover is basically a build to print of the Curiosity rover, and the entry system, which is going to land Perseverance, is also essentially a build to print of the Curiosity rover. So we learned so much from the Curiosity mission that we were able to leverage it, put it into Mars 2020, and demonstrate a few more precision techniques with landing, which we'll talk about during the course of the presentation. But this gives you a good idea of scale. So the Perseverance mission, what is it all about? So Mars Perseverance, Mars 2020, it's an astrobiology mission. The goal is to determine the habitability of the ancient environment of Mars billions of years in the past. So the rover is basically going to be searching for biosignatures. Biosignatures are chemical fossils which preserve the evidence of past life. Some examples of that would be isotopes or molecules that can only be formed by biological processes. The other unique aspect of the Perseverance mission is that the rover is going to cache a sample. It's going to collect a sample and store it so that one day we can pick up that sample and return it to Earth in a mission called Mars Sample Return. So one of the reasons why we want to do that is that although these rovers are amazing, they have fantastic scientific equipment on board, nothing beats an Earth-based laboratory to make those measurements. So if we can take that sample, which is collected by the rover, put it on something called a Mars Ascent Vehicle, rendezvous in orbit, bring it back to Earth, re-enter Earth's atmosphere, pick up that sample, take it to an Earth-based laboratory, we can learn more about ancient habitability on Mars than we've ever been able to do in the past. The other really important feature of the Mars Perseverance mission is to pave the way for the future human explorers, which is what we talked about, the secondary reason for wanting to go to Mars. And the way we're going to do that is by demonstrating a technique called in situ resource utilization, which is ISRU, which is the acronym. And there's an instrument on board called MOXIE, which is going to take the Martian CO2 from the atmosphere, carbon dioxide, split it up using electrolysis, and then create oxygen. If we can demonstrate that we can create oxygen on the surface, we can provide a way of human beings living off the land in the future when we have a Mars science surface mission with people. And also we can make rocket fuel as well. So it's really important that we can make those measurements with a robotic platform first. And of course, it has more traditional goals of characterizing the atmosphere and characterizing the properties of the rocks and the soil in the vicinity, which is in. So Perseverance is going to be a really important, fascinating mission coming up in the near future. So let's see if I can go to the next one. So where are we going to land? It's really important to pick a landing site location, which is interesting from a scientific perspective, especially because we're collecting a sample for future return. So NASA chose Jezero crater, which you can see here on the right-hand side as a landing site for the Perseverance rover. So the reason why we're so interested in Jezero crater is because planetary scientists believe the area was once flooded with water. It was the home to an ancient river delta. Jezero crater basically tells us the story of the on-again, off-again nature of the wet past of Mars. More than 3.5 billion years ago, river channels spilled over the crater wall and created a lake. So scientists see evidence that the water carried clay minerals from the surrounding area into the crater lake. So conceivably, microbial life could have lived in Jezero crater all those years ago in those wet times. And so by collecting a sample there, we might find evidence of ancient microbial life. So whenever we look for places where there's evidence of past water, we have sedimentary rock layers, which obviously are really interesting from a scientific perspective. And then the image on the left gives you an idea of where Mars 2020 Perseverance is relative to the other missions which have landed on Mars. People like to ask me the question, can the rovers drive to see each other? They can't, because they're such a far distance from each other, and they're also in a crater, and they don't have a way to be able to get out of the crater that they're in. But ultimately, the 2020 mission serves as future sample return, which is really important for human exploration, which comes next. So my area of expertise is actually how to land on the surface of Mars. And we do that with a combination of techniques with a discipline, which is a multidisciplinary field called entry, descent, and landing. The rover is packaged inside of something called an aeroshell, which is the picture that you see here on the left. It kind of has this really odd looking bowl shape. It has that shape for a very specific reason, because it generates aerodynamic drag. So with the interaction with the atmosphere and this odd looking shape, we can generate lots of drag to slow us down, which helps us go from a really fast speed of around 30,000 miles an hour to a much slower speed of around 2 miles an hour, using different means of creating aerodynamic drag and then eventually retropropulsion. On the front side of this thing, you see something which is a slightly darker color. This is known as a heat shield, and it's made of a very special material that stops basically it from burning up and protecting the rover inside, keeping it at a nice room temperature. This also, although it doesn't look like it, is a lifting body. It actually is a odd kind of airplane. So there's a slight lift to drag ratio, which means that you can modulate the lift vector of this aeroshell and actually fly the thing down to a more precise landing location. Of course, that's not done with a joystick because of the time delay between Earth and Mars. It's done autonomously by the flight computer on board the rover. So it doesn't look like a bird, but doesn't look like a plane, but it does have the ability to generate lift and do a lifting body entry, guidance, navigation, control in the hypersonic regime. So I've got a short video I wanted to show, and apologies if it doesn't come out that great, but you can find it online. This is the entry, descent, landing sequence. Coming in really fast, slowing down from hypersonic speeds to supersonic speeds, then deploying a very large supersonic parachute, which was my portion of the mission during Curiosity that I worked on. That slows it down from around 1,000 miles an hour to about 250 miles an hour. At that point, you've actually hit terminal velocity on the parachute. So you cut the parachute away. And then the descent stage, which is a little spacecraft with 8 rocket engines on it, then descends towards the surface, firing its engines, slowing itself down to around 2 miles an hour. Now, when you get to around 60 feet above the surface, you start to lower the rover on a tether. This is called the sky crane maneuver. This was developed specifically for the Curiosity rover. It's also being used for the Mars 2020 rover. And then the rover is able to descend safely towards the ground, where it touches wheels down, and the entry, descent, and landing segment is complete. Those tethers are cut. The descent stage tilts off to the side, glides away, and now the rover is set to do its surface mission. So this was the technique that was used by the Curiosity rover successfully in August of 2012, and it's the pretty much exactly the same technique which is going to be used for the Perseverance Mars 2020 rover coming up in February of 2021. This is another way of looking at that same entry, descent, and landing segment sequence, where you start off in these hypersonic speeds with a heat shield, slow down to supersonic speeds, pop a parachute, slow down to subsonic speeds, then get rid of the parachute and use retro rockets and the sky crane to safely land the rover on the ground. These techniques are key for robotic exploration, and many of them can also feed forward for future human exploration and all the data which gets collected from all the different hardware as we do this. So the future for rovers and the future for human Mars exploration oftentimes is coupled to advanced power systems. And so this is a picture of the Perseverance rover. Over a period of 5 years, NASA engineers and scientists built and tested this rover to ensure that it could do its science surface mission job, as well as survive both during the cruise in interplanetary space, during the entry, descent, landing sequence, as well as on the ground. So you can see it has large movable wheels that enables it to traverse very complex terrain and large rocks, which enable interesting scientific investigation. And unlike the rovers that came before Curiosity, which had solar power, this rover has a nuclear power source, has something called a MMRTG, a multi-mission radioisotope thermoelectric generator. So it has nuclear material on board, plutonium-238, which decays. You use a special technique to convert that into electricity. So it basically has its own battery that generates power that it can use 24 hours a day for many, many years, which facilitates a more complex surface mission as a result. So how long does it get to take to Mars? The goal is to always be on a minimum energy trajectory, and that is typically somewhere between 7 and 9 months, depending upon the launch opportunity. So the Mars Perseverance mission, or Mars 2020, launched this past July, and it will reach Mars for its entry, descent, and landing sequence on February 18th, 2020. After it lands, it will have a minimum of a 2-year surface mission, and it likely will expend many years beyond that, just like Spirit and Opportunity did, and just like Curiosity has done. So I'm sure we're looking at least a decade worth of science, which is one of the really unique aspects of a rover mission versus a lander mission, because the rover can keep on moving to different locations within its crater and collecting more interesting scientific information. So in terms of the essentials for a robotic geologist, whether you are a person or a robot, you want to do science. You want to carry a lot of really interesting science equipment. So it has cameras to be able to take images, both for hazard protection as well as for scientific purposes. It also has a spectrometer, which will allow it to determine chemical and molecular composition to look for those biosignatures. And then it has the MOXIE experiment, which will allow it to produce oxygen from Martian CO2 by electrolysis to demonstrate that in situ resource utilization technique. It also has a robotic arm, which allows it to go out and make measurements just a short distance away from it. So one of the other videos I wanted to share is something which is we developed during the Curiosity landing. So let's see if I can get this to go. This is a camera called the Marty camera that looked straight at the ground as the rover descended toward the surface. What you saw just then was the heat shield falling away, and now you see the rover looking down towards the surface of Gale Crater, which is where the Curiosity rover landed. You can see a darkened region there. That's evidence of past volcanic activity, or sort of like lava flows on the surface, volcanic deposits. And you can see it's moving slightly, the field of view. And the reason for that is because the rover is currently hanging under the parachute as it's descending towards the surface. And anybody who's ever flown on a parachute before knows that you get some kind of rocking oscillatory motion. So as it's collecting these images, it was doing this for a technology demonstration purpose, but it did it for a very specific reason, because now in the Mars 2020 mission, a very similar technique of having a camera looking towards the ground, making measurements of where you are on the surface by the visual images compared to a map that the rover already has on board its computer. It's able to use a technique called terrain relative navigation to more accurately define its landing location on the surface. At this point in the video, what you're seeing is the rover descending. The parachute is gone. Now it's just using its retro rockets to fly around to get closer to its landing location. And now you're seeing it getting very close to the ground. So its rocket engine plumes are actually interacting with the soils. And now you can no longer see the ground because of that. So this was done for technology demonstration to feed forward to the Mars 2020 mission Perseverance, coming up in just a few months' time. And that was a very successful technology demonstration, which we can now use as part of the overall entry, descent, and landing system. So terrain relative navigation, a technique that we demoed with Curiosity, is now being implemented with Perseverance. It enables us to have a much more precise landing location. It adds to safety of the overall entry, descent, landing sequence. And the goal, of course, would be to facilitate a pinpoint landing, which is something which is needed for future human Mars exploration, so that the crew can land on a landing pad close to where their habitat is, close to where all their supplies are. So the robotic space exploration program feeds forward into the human exploration mission. So right after landing of the Curiosity rover back in 2012, the rover was commanded itself it had to send an image back of its landing location, which we were able to see. And you can see sort of the mountain in the distance, which is the place where it actually has been driving over the course of the past 8 years to be able to visit more interesting locations along the way and take scientific measurements. But what I like to point out in this video, of course, is that it looks so similar to the deserts here on Earth. So the terrestrial planets are, in a sense, very similar to each other. So although there isn't any oxygen, appreciable on the surface, you can see how you wouldn't feel so far away from home if we were to live there as a species. One of the important measurements that the Curiosity rover has on board is making measurements of the atmosphere and making measurements of the radiation environment at the surface. Unfortunately, the radiation environment is actually quite bad. But now that we know what it is, we can design radiation shields so that people can be protected from it when we eventually send human beings to live on the surface of Mars, I hope. So Mars sample return is what is the goal of the Mars 2020 mission. And this shows you a graphic of a very powerful instrument that was on board the Curiosity rover, which it fired a laser. You might have seen it on social media where people had a hashtag of pew pew, which was a laser burning a hole in a rock. It generates a vapor. That vapor has a certain spectroscopic signature to it, which is a fingerprint, which tells you what the rock is made up of in terms of its elemental composition. So this type of measurement technique, which we demonstrated with Curiosity, can also be used for all future Mars explorers to be able to determine what the composition is of the rocks and the soil that they're taking a look at. Now, of course, one of the wonderful instruments that's on board Perseverance is this MOXIE instrument, which allows us to create oxygen from Martian CO2. Once again, another technology demonstration necessary for the future human exploration of Mars. Another key technology which is being demonstrated on Mars 2020 Perseverance rover mission is the first time ever flight of an electric vehicle on the surface of another planet, and specifically an electric airplane, or I should say rotorcraft. So the Mars 2020 mission has a helicopter and is known as the Ingenuity helicopter. And because the atmosphere of Mars is very thin, it means that the helicopter had to be quite light. So everything was lightweighted, but fortunately the gravity is lower too. So you are able to have a helicopter that operates on Mars. It has a very short window of being able to operate per day, about 90-second flight time, and then it goes back and recharges itself. But we'll be able to get amazing reconnaissance images of the surface with this helicopter, which is flying above. And if this works out, you'll probably see a helicopter or something like it on future missions to Mars. So once again, this technology demonstration, very challenging, unique implementation of a rotorcraft. So to wrap up the presentation before we take questions, I wanted to focus on what technologies do we need to put the first humans on Mars? This obviously is the technology track, so it seemed like something that was important. One key one is something that we have been developing and have to develop even more so is autonomous systems, because when you have robotic explorers, you can't have a person in the loop controlling it because of the time delay between Earth and Mars. The further out you go to other locations in the solar system, that comes even bigger of a challenge. And also for the entry, descent, landing sequence, it happens so quickly, it also has to be done autonomously. So the autonomy has a hardware component to it, but of course it has a massive software component to it from a guidance, navigation, control, and a hazard avoidance perspective. The other key, of course, are the vehicle technologies that are going to take people here. So human space travel beyond LEO, beyond low Earth orbit. It's in development on the government side with the Orion vehicle, which you can see me standing in front of. A bigger version of Apollo is the way you can think of it. And it's also under development for access to the space station with companies like SpaceX, Boeing, and Blue Origin, for example. So we have to have these technologies, which are slightly larger in scale than robotic technologies, to be able to send people safely to the surface of other planets. And these types of vehicles would be used for interplanetary crews, as well as the entry, descent, and landing segment. Another really important piece, though, of the human exploration of space in general, beyond the protection of the Van Allen belts here on Earth, which is our magnetic field, is radiation protection. There's two sources of radiation, from the sun and from deep space. And so we do need to develop radiation shielding technology for future human exploration, both the interplanetary crews as well as living on the surface of Mars. And I like to give my example here of Shields Up from Star Trek. So maybe we need something like that. We need some kind of shield, which comes from a magnetic field that we generate on the vehicles. That's an area which is ripe for new technology development to keep people protected as they transit through space from those high energy radiation particles and electrons, as well as ions. Another key is artificial intelligence. We're only going to have people do extra vehicular activities when we have to. So when we can use robots to do more mundane tasks or even complicated tasks using artificial intelligence, that's something that we would opt for, because then it would protect the people and have the people only there to do those sort of EVAs for the most complex tasks that an artificial intelligence in a robot wouldn't be able to handle. These are obviously in development at NASA that you can see here with Rover, and they're also in development across the multiple economic sectors for different varieties of economies. So you can see sort of an intersection there with artificial intelligence, AI, things that might be used in the private sector and things that might be used for future human exploration of space. Another important one is growing food. So obviously, if we are going to set up a colony on the surface of Mars, we're not going to, it doesn't make sense for us to bring all of our food with us from Earth. That wouldn't be that efficient. Any of you who have read the book The Martian or watched the movie The Martian remember that Mark Watney grew potatoes. So we will absolutely be growing vegetables on Mars. We can use the Martian sunlight as a means of photosynthesis, right? Providing the radiation from the sun to enable photosynthesis. And then we can also use the CO2 from Mars to facilitate photosynthesis as well. And those same plants could also make some oxygen. It's very likely, however, because of the radiation environment on the surface, that much of the habitation would be subterranean in caves or under some kind of soil brick structure. And so you can see demonstrated here a greenhouse, which is fed with light through fiber optics to be able to grow food on the surface of Mars. And absolutely everybody will be vegetarians on those missions, because that's the type of food that you'll be able to grow. You won't be bringing animals with you unless you're eating an Impossible Burger, which is still vegetarian. So there is technology which is being demonstrated now for that, which is on the International Space Station. It's called the Veggie experiment. And so you can see images of that, of little lettuces which have been grown on the International Space Station. The real challenge, however, is that plants don't grow so well when they don't have gravity, because they don't know which way is up, which way is down. They don't know where to put their roots. So it's been hard to grow good looking lettuces on the International Space Station. But fortunately with Mars, there is the 1/3 gravity, which means that it'll be a little bit easier to grow food there. This is an example of how you could grow food in a more hydroponic sense, as opposed to just doing it traditionally in the soil. Now, the first humans on Mars will be living in really small colonies, in small habitats. This gives you an example of sort of an artist's conception of what one of those would look like. And then on the right is actually a demonstration from an Arctic research base where people test out what is it like to live in a small space for long periods of time from a human interaction and sort of a mental health perspective. But we have to be able to live off of the land, use in situ resource utilization here on Earth in these demonstration experiments before we actually do it on the surface of Mars at some time in the future. If we do go to Mars, it would be terrible if we didn't have a car. So certainly surface mobility is part of one of those new technologies. It would have to be a pressurized rover that can carry people to take you from the habitat to another location to do scientific experimentation and then come back. This is also under development that you can see here in a rover which was being developed at NASA Johnson that I had a chance to check out. And something like this is something that would be on the surface of Mars. Of course, you'd either be in a spacesuit or you would have a pressurized cabin that goes over the drivetrain, for example. But ultimately, in situ resource utilization is the key. You want to use the sun for power. You want to use the regolith or the subterranean environment for radiation protection. You want to be able to get water from those subsurface aquifers, and then you want to be able to potentially make rocket fuel either out of methane or out of O2 and H2 from those subsurface aquifers. And growing plants called extremophiles, which be very little oxygen, but will use up the CO2 and create oxygen themselves. So to wrap it up, this is maybe what a colony would look like in 100 years from now, when you have multiple habitats and people living together in a small community. And I think the question would be, do you want to go to Mars based off of what I talked about today? So I think we've got about 6 minutes left for questions. And if I don't get to your question, certainly you can contact me via Twitter. That's the easiest way to reach me. And let's see, what kind of questions do we have here so far?
Okay, please post your questions in the session Q&A if you have any questions.
I'll get the first one, which says, is there an expected timeline for humans on Mars? So the challenge is twofold. One is you have to have enough money to be able to support a mission like that. And the second one is you have to develop the technologies and demonstrate and validate and qualify those technologies. And those two are very much coupled to each other. So if you had an infinite supply of money, I could see it happening in the next decade, but you don't have an infinite supply of money. So I would say probably in the next 10 to 20 years, if space agencies from around the world work together and commercial entities work together, we could see the first people on Mars in the next 20 years, I think is actually quite feasible. But once again, it is tied to how much money we have. The second question is, I'm thinking about Hidden Figures, and I'd love to know how inclusive and diverse such teams are and what is being done to make them more so. Hidden Figures was a fantastic movie for so many reasons. I think it was inspirational to women, certainly inspirational to me, inspirational to next generation girls, and inspirational to people from underrepresented groups. NASA actually does a surprisingly good job at having diversity in its workforce. So they deserve a lot of kudos for that. So you see people, from the leadership side to the engineering side, and they do a really good job with that. I would say the aerospace industry in general, however, does not. So I spent my whole career in aerospace, and there are often times where I would be the only woman in a group of 40 or 50 people. And then as you go up the food chain, for lack of a better term, into the leadership structure, you also see fewer and fewer women, and you also see fewer and fewer people from underrepresented groups, which I think is terrible. So I think the way we solve that problem is by making hiring decisions at a corporate level, that we have to have diversity in our engineering teams, in our science teams, in our information technology teams, whether that be women or people from underrepresented groups. I think it has to come from the top as a goal from the corporate. And I think some companies are doing a good job out of it and some companies aren't. And I would say that the startup space probably doesn't do a good job at it, unfortunately. But yeah, it's something that's very important. And I think we all have to think about that in terms of if we become hiring managers. Next question is, would transportation on Mars run on H2? So it certainly, if you had access to a water source, like if you were to set up your first colony, close to where one of these subsurface aquifers was, and you could tap into it, you could certainly tap into the H2O, and you would make hydrogen and oxygen off it, and then you have rocket fuel. You have a fuel and an oxidizer, so that's perfect. The other proposal, however, is to make methane, where you bring a supply of hydrogen with you, and then you combine it with the CO2, you make methane, which is also a type of rocket fuel. I think what would probably happen is that you would have fuel cells. So you would have a hydrogen supply that either you brought with you or you created by electrolysis, and you would have a tank on board, sort of like a hydrogen fuel cell car. I think that's probably the most likely scenario or you would simply just have batteries, and then the batteries would be recharged by solar farm that you have on the surface. But you do need to have stored energy on these vehicles. So maybe you'd start off with batteries, and then maybe you would shift over to hydrogen fuel cells. That's probably my guess. I think those were the only three that I saw. So anybody else have another question you want to ask? We've got another 2 minutes left. I don't see one. So I think it looks like that's it. I think what I would say is everyone pay attention for February 18th. So I'm sure there'll be a lot of coverage from NASA to watch it on NASA TV, to be able to watch the landing. And for those of you who missed it, there was actually a landing on an asteroid yesterday to collect material in a touch and go called OSIRIS-REx, another NASA mission. All that information is out there in social media. But thanks everyone, and it was fun talking to you.
Thank you, Dr. Sengupta, for your presentation, and I'd like to thank the attendees for joining today's presentation. We appreciate the questions that came during this session. Please contact the speaker if you have any further questions regarding this topic. She mentioned using Twitter. I hope you gained some insight from this session. I actually did. That was a very interesting subject. Please provide your comments and feedbacks to us, and have a wonderful evening. And thank you for being part of this year's DataCon LA. Thank you, Dr. Sengupta.
Bye-bye.
Bye.
Have fun, everyone.